High-performance AI is transforming industry, but every breakthrough comes with a growing energy cost. AI4Labs exists to reduce that footprint without compromising the computing power modern organizations depend on. Inside a new generation of AI research labs, efficiency is no longer a side goal. It's an engineering requirement that shapes how clusters are powered, cooled, and scheduled in real time. AI4Labs brings those layers together through sustainable engineering and intelligent automation, creating infrastructure that is faster to optimize, more stable under load, and more responsible by design. The challenge starts with demand. As AI models grow larger and training cycles run longer, GPU clusters draw massive amounts of electricity around the clock. That energy doesn't just disappear into computation. A significant share becomes heat, which raises thermal stress across racks, power delivery systems, and cooling infrastructure. When utilization spikes unpredictably, voltage demand, fan response, and cooling loads can all surge together. That makes performance management harder and efficiency losses easier to miss. For ISO-certified organizations, this matters beyond cost. Energy intensity, thermal stability, and environmental performance are now part of a much broader operational responsibility. The result is clear. More AI capacity can mean more emissions, more infrastructure strain, and more pressure to prove that performance gains are being achieved responsibly. One of the most effective levers is dynamic voltage scaling. Instead of feeding hardware at a fixed electrical profile, AI4Labs adapts voltage and frequency to the workload as training unfolds. During different phases of training, not every GPU operation needs peak voltage. By matching electrical input to actual computational demand, the cluster avoids unnecessary power draw. That means less energy wasted as excess heat. It also reduces the thermal load that would otherwise ripple through adjacent components and cooling systems. Because the adjustments happen in real time, performance stays aligned with workload needs instead of relying on a static safety margin that runs hotter than required. The benefit isn't just lower consumption. Smoother voltage behavior can improve hardware utilization by keeping systems within more stable operating conditions across long training jobs. In practice, AI4Labs turns power delivery into an intelligent control layer. The cluster computes what it needs, when it needs it, with far less electrical waste along the way. Power efficiency only solves part of the problem. In dense AI environments, heat removal has to be engineered just as carefully as computation itself. That's where liquid cooling changes the equation. Coolant can move heat away from high-load components far more efficiently than air alone, especially inside tightly packed GPU racks. With better thermal transfer, clusters can sustain heavy workloads with fewer hotspots, lower temperature swings, and less dependence on aggressive fan-driven airflow. That thermal stability matters during long training runs, where even small fluctuations can affect performance consistency and increase stress on surrounding infrastructure. It also supports higher compute density. When heat is removed more effectively, organizations can deploy more processing power within the same physical footprint. Over time, cooler and more stable operation can extend hardware life and reduce maintenance pressure. AI4Labs uses liquid cooling as a core reliability strategy, not just a thermal upgrade. AI4Labs adds a third control layer through carbon-aware scheduling. This is where infrastructure decisions begin to reflect not just performance, but also the carbon intensity of available electricity. When renewable energy availability rises in a region, certain training or inference workloads can be shifted to run during that cleaner window. When grid carbon intensity increases, non-urgent workloads can be delayed, redistributed, or sequenced differently to avoid unnecessary environmental impact. This does not mean sacrificing operational control. It means using scheduling intelligence to balance service requirements, compute deadlines, and sustainability targets at the same time. For organizations measured against environmental commitments, that visibility is critical. It creates a clearer link between workload orchestration and measurable emissions reduction. In effect, AI4Labs helps clusters run when energy is cleaner, not just when servers are available. That turns scheduling into a practical sustainability tool. What makes AI4Labs different is how these systems work together. Dynamic voltage scaling reduces waste at the chip level, liquid cooling stabilizes the physical environment, and carbon-aware scheduling optimizes timing at the grid level. Together they form a coordinated efficiency architecture. Power, temperature, and workload orchestration are no longer separate problems managed in isolation. That integration supports stronger operational consistency, better resource utilization, and a clearer sustainability story for stakeholders, customers, and auditors. The result is high-performance AI infrastructure that can scale more responsibly as demand grows. Performance remains essential, but efficiency becomes built into every layer. For organizations pursuing both innovation and accountability, that's the real shift. Sustainable computing stops being an aspiration and becomes an engineered capability. AI4Labs shows that advanced AI infrastructure can be powerful, thermally stable, and environmentally responsible at the same time. That's the future of high-performance computing, and it's already taking shape. If you're ready to make your AI clusters more efficient and sustainable, visit www.ai4labs.org.